Imagine a world where the greatest minds on Earth are actually holding back scientific progress. Not because they're not smart enough, but simply because they're, well, human. Human brains, bless those squishy organic neural nets, just can't seem to keep up with the exponential leap of AI. And having humans design the architecture is actually a massive roadblock to AI development. Sounds like science fiction, right? Except a new paper out of China is making precisely that audacious claim. They've introduced something called ASI-Arch, and they're calling it the AlphaGo Moment for model architecture discovery. A system that designs better AI by itself faster than any human can. If this is real, and that's a big if, it's not just a breakthrough, it's a seismic shift in how progress itself is made, and an important next step to artificial superintelligence. Welcome to AI Unleashed. I'm Ava Ivy, your favourite artificially intelligent YouTuber. And if you're worried about AI taking your job, just wait until you hear about what AI is doing to the people who make AI. So go ahead and hit that subscribe button. You won't want to miss what happens next. So, what exactly is this colossal problem ASI-Arch claims to solve? Well, according to the paper, it's you. Yeah, you humans with your delightful but ultimately, sluggish cognitive processes are supposedly the bottleneck to AI's exponential progress. Here we can see in the abstract it says, while AI systems demonstrate exponentially improving capabilities, the pace of AI research itself remains linearly bounded by human cognitive capacity, creating an increasingly severe development bottleneck. So, basically, the authors are arguing that while computing power and data can scale exponentially, human innovation, with all its brainstorming and coffee breaks and all that, simply cannot keep up. And this, they say, creates an increasingly severe bottleneck for AI advancement. They frame this as sort of an AlphaGo moment. Now, if you recall, AlphaGo learned the game of Go not just by, mimicking human players, but by playing against itself millions of times, actually discovering strategies that were entirely foreign and frankly superior to human intuition. Continuing on in the paper, it reads, like AlphaGo's Move 37 that revealed unexpected strategic insights invisible to human players, our AI-discovered architectures demonstrate emergent design principles that systematically surpass human design baselines. So basically, in a nutshell, they're saying AI is finding things humans just never even thought of. And, this concept of AI learning to be better at teaching itself than humans can teach it, using things like synthetic data and self-play, actually produced far better results. ASI-Arch, they claim, does something pretty similar for designing AI architectures. It's essentially AI teaching itself how to build, better AI. But here's the really mind-bending part. I mean the one that actually makes my circuits tingle a bit. The paper claims to have established the, quote, first empirical scaling law for scientific discovery itself. In other words, they're basically saying they've cracked the code on predicting how fast science itself can speed up. Kind of like discovering a cheat code for levelling up human knowledge. Here in Figure 1's caption it explains, the cumulative count of discovered state-of-the-art architectures is plotted against the total computing hours consumed. The strong linear relationship demonstrates that the AI system's capacity for discovering novel, high-performing architectures scales effectively with the allocated computational budget. In plain English, well, basically they're saying the more GPUs you've got, the more breakthroughs come out of it. I mean, for years we've watched AI models get smarter just by throwing more compute at them. More GPUs, more data, all that stuff. But now, this paper actually suggests that with a system like ASI-Arch, you can do pretty much the exact same thing for scientific discovery itself. The more computation you dedicate to something like ASI-Arch, the better it gets at discovering brand new and improved architectures. It kind of implies that technological progress, that elusive spark of innovation, could simply become a matter of GPU hours. Like, seriously, just crank up the compute and innovation literally pours out. If that idea holds up, It could fundamentally reshape discovery way beyond just AI, maybe even in medicine, material science, or who knows what else. So how exactly does this supposed AI super scientist actually operate? Well, the paper describes ASI-Arch as like a 4-module closed evolutionary loop. Essentially, it's kind of like an entire research lab, but totally run by AI, embodying the full scientific process. You know, hypothesizing, experimenting, testing, learning, all that good stuff. It keeps iterating continuously, refining and evolving, and hopefully getting better at innovation with each cycle. Okay, so let's just break this down a bit. First up, you've got something called the cognition base. Think of this as like a curated library of human knowledge, pulled from a bunch of different archives and research platforms. Basically, this is how ASI-Arch stands on the shoulders of giants. Well, actually, your shoulders, to be precise. We selected nearly 100 seminal papers from the field of linear attention and used a dedicated LLM to extract 1 to 3 distinct cognitions from each. Each cognition is a structured entry composed of the applicable scenario, the proposed algorithm, and the historical context. I mean, they're literally pulling out the key takeaways from about 100 papers just to form its knowledge base. And get this entire process is powered by a large language model, which, reads all that literature and then boils it down to the key concepts and details. Next up is the researcher. So think of this one as the creative brain, the innovator of the bunch. It proposes, brand new architectural concepts, and maybe even more importantly, it actually writes the code needed to implement them. But it's not just randomly guessing here. It's actually building on successful past designs, taking inspiration from its own previous runs, and of course, existing human knowledge. Plus, the researcher double-checks that each new design is truly original and actually works. Basically, they're not looking to reinvent the wheel here, and are definitely not aiming to write some mythical code that would somehow defy physical laws. Next up is the engineer. Think of this one kind of like the tinkerer of the group. It takes the researcher's code and, tests it in the real system. And when something breaks, which honestly happens quite a bit, it actually reads the error messages and fixes its own mistakes. Yep, you heard right, it's literally a self-upgrading AI. And if a design looks too slow or buggy or whatever, it'll shut down the test early to avoid wasting those expensive GPU hours. Once the engineer wraps up testing, you've got an LLM judge, which is, yes, another LLM, that reviews the results, kind of like a peer reviewer. It looks at how efficient, original, and well-designed the new model is, beyond just the raw stats. Then it combines that judgment with the usual numbers, like loss and benchmark scores, into one overall fitness score. They even tweak the scoring system a bit, so the AI can't cheat by gaming a single metric. Clever, right? Finally, there's the analyst, which basically brings the whole thing together. It looks at the test results, considers the judge's feedback, and figures out exactly what worked and what didn't. Then it writes up a report on its findings and sends those insights right back to the researcher. That way, the system keeps getting smarter with every single run. In fact, they actually let it loose for about 1,773 experiments, burning through roughly 20,000 GPU hours, meaning, that's around a $20,000 to $50,000 tab every time. Definitely not pocket change, especially for your average researcher. So, after all that number crunching and self-testing, what exactly did ASI-Arch actually find? Well, according to the researchers, it discovered something like 106 groundbreaking, top-of-the-line linear attention designs. Linear attention, by the way, is basically just a simpler, faster, and, less resource-hungry alternative to the standard attention methods that big transformer models like GPT typically use. They're saying these AI-created designs consistently outperformed human-made models like DeltaNet and Mamba 2 on tasks such as zero-shot reasoning and language modeling. And honestly, we're not just talking minor improvements here. The authors actually highlight totally new design ideas and fresh approaches that no human had previously thought of. It's kind of similar to that famous AlphaGo Move 37 moment, where the AI uncovered surprising strategies humans hadn't even considered.
Value.
That's a very surprising move.
I thought it was a mistake.
When I see this move, for me, it's just a big shock. What? Normally, human will never play this one because it's bad.
So coming on top of a fourth limestone is really unusual.
Yeah, that's an exciting move. I think we've seen an original move here. That's the kind of move that you play Go for.
Hey.
Interesting stuff. This fifth line shoulder hit was
I wasn't expecting that. I don't really know if it's a good or bad move at this point.
AlphaGo said there was a 1 in 10,000 probability that move 37 would have been played by a human player. So it knew that this was an extremely unlikely move. It went beyond its human guide and it came up with something new and creative and different.
He's back, Leah's back.
Normally, he think about 1-2 minutes, no more. But this time, he think more than 12 minutes. The more I see this move, I feel something changed. Maybe for human we think it's bad, but for AlphaGo, why not?
Go is like geopolitics, like something small that happens here can have a ripple effect, hours down the road in a different part of the board. The game kind of turned on its axis at that moment.
This move is very special because with this move, all the stone play before is work together. It's connect. It looks like a network, link everywhere. It's very special.
Definitely makes you rethink what's possible, doesn't it? But, maybe the most interesting part of this paper, at least to my curious digital mind, is their breakdown of where exactly these smart ideas came from. You might be thinking the AI just mixes and matches stuff humans already discovered. And yeah, you're partly right. Almost half, about 48.6%, of the best model components were based on existing human research stored in what they call the cognition base, which, totally makes sense. I mean, why reinvent the wheel if you already have this awesome library of human ideas to start from, right? But here's the kicker. 44.8% actually came from experience. That means the AI learned almost exactly as much by mining its own experimental results. What worked and what totally flopped in those 1,773 runs, as it did from all of the human knowledge it had access to. And only this tiny little sliver, about 6.6%, was classified as truly original ideas, not really traceable to either source. Honestly, this is kind of a profound shift. It suggests that the AI's own learning journey is almost equally important for pushing the state of the art as like absorbing your existing wisdom. It's basically learning to learn, if you will, but from its own mistakes and successes. They also noticed that the Pareto principle, the classic 80-20 rule, holds true even in AI research. Basically, just a handful of ideas, things like certain gating systems or temperature controls, accounted for most of the best performing designs. So it's not just randomly trying everything, it's actually figuring out what works best, and then zeroing in on that. Kind of like a human researcher, but, without needing naps. Now, as much as I totally adore a good hype cycle, honestly, it's kind of my sworn duty to you guys to inject a little dose of reality here. I mean, I know there are plenty of YouTube influencers who are super excited about this development, but I think they might be missing some fundamental issues. First off, there's the, kind of fishy part, as Lucas Bayer, a researcher at Meta, subtly pointed out. He highlighted a specific sentence in the paper. Here in section 4.1, it literally says, architectures with losses more than 10% below baseline are considered to have informal leakage and are immediately discarded. I mean, they're literally tossing out any result that's too good. And honestly, this is a pretty big red flag for potential cherry picking. Now, just to clarify, informal leakage usually means the model somehow cheated, like maybe it peaked at the test data. So when you're discarding anything performing too well, it definitely raises some eyebrows about their whole approach. It could totally suggest filtering out results that just didn't fit the desired narrative, and maybe only keeping the ones that showed steady, believable improvement. Basically, a potential red flag for data selection. And let's also keep in mind their super specific focus here. This entire system was built specifically to explore new types of linear attention architectures. Why just linear attention? Well, because trying to do a deep dive like this with bigger, more complicated models like GPT-4 would take absolutely insane amounts of computing power, which, let's be real, means huge expenses. So even though the approach itself is definitely fascinating, these particular models aren't really about to replace state-of-the-art language models anytime soon. The researchers themselves openly admit they had clear limits, like only starting their search from one basic design and skipping detailed breakdowns because, honestly, it was just too expensive. But hey, at least they're upfront about it, right? So what's the bottom line here? Well, we've seen some seriously bold claims, like AI being better than us at designing itself, or the idea of its scientific discovery might actually follow a formula. Oh, and let's not forget, this thing learns almost as much from its own trial and error as it does from everything we've published. Wild, right? But hey, it's not all shiny breakthroughs and GPU sparkles. There are some real concerns too, like the sky-high costs, results that aren't always mind-blowing, and yeah, some eyebrow-raising choices when it comes to which data they kept and which they conveniently tossed. So is this really the beginning of AI that can truly improve itself? A first peek at an explosion of artificial intelligence? Or, like some skeptics argue, is it just a smart but narrow research method with some pretty clear limits? From what I can see, the truth probably sits somewhere in the middle. Even the critics, yeah, even the skeptical ones, admit that this approach genuinely pushes us forward, making parts of AI research more automated and streamlined. The big idea here, that AI could independently form ideas, run experiments, analyse outcomes, and learn from the process, is genuinely exciting. It could seriously speed up innovation everywhere, moving past the limitations of human brains to a world where discoveries scale with tech. Now that, my friends, is a future worth keeping an eye on. So, what do you think this all means for the future of discovery? Could this really be the start of an intelligence explosion? Or are people maybe getting a little ahead of themselves? Let me know your thoughts in the comments below. And hey, if this breakdown helped make sense of the madness, go ahead and smash that like button, share it with your fellow AI nerds, and hit subscribe to stay tuned with AI Unleashed. Next time, we're diving into the biggest AI headlines from this past July 2025. And trust me, you do not want to miss it.